Hi there, this is Nuclear Physics Lesson 7, and this is Half-Life and Decay practice questions. So let's have a go at this one. If you want to pause and have a go, then I'll take you through the answer. Cobalt-60 has a half-life of 5.27 years. What is the total activity of 1 gram of cobalt-60? So I want activity, so activity is lambda n. So we need both the decay constant and the number of nuclei. So let's do the decay constant first. So decay constant is equal to log 2 divided by the half-life. So log 2 divided by, now the half-life is 5.27 years. So let's change that into seconds to get decays per second. So that'll be 5.27 years multiplied by the amount of days in a year, which is 365, multiplied by the amount of seconds in a day, which is 60 seconds times 60 minutes times 24 hours. So 60 times 60 times 24 hours is 86,400 seconds in a day. So that gives a decay constant that's equal to, now I'm going to use quite a lot of significant figures, 5 for an intermediate calculation, 5.1707 times 10 to the minus 9, s minus 1. Now let's calculate the number of atoms. So I'm going to make sure you've got this written down if you've not got this. Now let's do the number of atoms. So we've got cobalt-60, so that'd be 60 grams. So 60 times 10 to the minus 3 divided by Avogadro's number, 6.02 times 10 to the power 23. And that gives us 9.967 times 10 to the minus 26 kilograms. So that's the mass of a single cobalt-60 atom. Then we've got a gram, so we need to do 1 gram divided by the mass of a single atom. So 9.967 times 10 to the minus 26. And that'll give us the number of atoms, which is 1 times 10 to the power of 22. Hopefully that's okay. Then we just need to do activity is lambda n. So 4.1707 times 10 to the minus 9 multiplied by 1 times 10 to the 22. And that gives us an activity of 4.2 times 10 to the power of 13 becquerel. Hopefully that one went okay. Let's move on. So this one just says change the exponential decay equation into a linear format. So I'm going to give you a graph that you could typically plot. So I'm going to ask you to plot log n against time. I know you to pause the video and try and figure that out. So we're going to turn the exponential decay equation into a straight line. So that would be, the equation is n equals n naught e minus lambda t. And what we can do is log everything. So we end up with log n equals a log n naught minus lambda t. Then we've essentially got it. So it's in the form y equals mx plus c already. We could actually tidy it up slightly. We could write log n equals minus lambda t plus log n naught. So that would be on the y-axis. Time is obviously on the x-axis. The lambda is the coefficient of x, which is the gradient n, and the log n naught is the plus c-intercept. So that's in the form of a straight line, so we should get a graph that looks like this. So that's just in case you see that, or you're asked to plot something in an exam, but that's how you do it. Okay, let's move on. A couple of descriptive questions. So what is meant by the random nature of radioactive decay? And then explain what is meant by each of the following: radioactive half-life and radioactive decay constant. So there's 3 questions there if you want to pause and have a go. So random nature of radioactive decay. So decay is random, cannot be predicted at an individual level. So each individual atom, it's impossible to say when an individual atom is going to decay. It's not affected by temperature, pressure, or environmental conditions in any way. It is truly random. Explain what is meant by each of the following. Radioactive half-life. It's the amount of time taken for half the given nuclei within a sample to decay. Radioactive decay constant. The amount of time taken on average for an individual atom to decay. So that's the S-1, per second, or year to the -1 per year, etc. Let's pause and have a go at this one, and then I'll take you through the answers. So first of all, I want to find the decay constant. Quite straightforward. So the decay constant is equal to log 2 divided by the half-life. So 8.04 days. Multiplied by the amount of seconds in a day, which is 60 times 60 times 24, which is 86,400. So that gives us a decay constant of 0.9978 times 10 to the -6. Let's move on, let's do part 2. So the number of atoms in iodine-131 necessary to produce a sample with an activity of 5 times 10 to the 4 becquerel. So activity is lambda n. So activity divided by the decay constant will give us the number of atoms necessary. So the activity is 5 times 10 to the 4 divided by the decay constant, the 0.9978 times 10 to the -6. So that will give us the number of atoms, which is 5.011 times 10 to the power of 10 atoms. Let's do the last one. So we've got activity falling over time. So A equals A0. E minus lambda t. And we want the amount of time, so we need to rearrange to find time. So we need to log everything, so it's log A minus log A0 minus lambda t by the log A, equals, log A equals log A0 minus lambda t. Then we need to rearrange it. So what we need to do is to find time. So we can do log A minus log A0. Sorry about that. Equals minus lambda t, and then divide by the decay constant. And that gives us the time. So let's put some numbers in. So it's log the activity, 5 times 10 to the 4, minus log of 5.4 times 10 to the 4, divided by the decay constant, which we just calculated in part 1, so minus 0.9978 times 10 to the -6. That gives a time of 77130 seconds, 77,130 seconds. And if we divide that by the number of seconds in an hour, which is 3,600, we end up with a time of 21.4 hours. So a bit tricky that one, but hopefully that went okay. I've got one more. Let's try this one. So the carbon content of living trees, if you want to pause please to have a go, please feel free to do so. The carbon content of living trees includes a small proportion of carbon-14, which is a radioactive isotope. After a tree dies, the proportion of carbon-14 in it decreases due to radioactive decay. The half-life of carbon-14 is 5,740 years. A piece of wood taken from an axe handle found on an archaeological site has 0.375 times as many carbon-14 atoms as an equal mass of living wood. Calculate the age of the axe handle in years. So the first thing we need to do is to find the decay constant, and we might as well keep it in years as it wants the age in years. So the decay constant is equal to log 2 divided by the half-life, which is the 5,740 years, which will give us a decay constant in years of, or per year, 0.1208 times 10 to the minus 3 years to the minus 1. Okay, so if you've got that, well done. If not, just write this down. Then we need to use the exponential equation. So activity is equal to the initial activity, E minus lambda t. So the activity is 0.375 times the initial activity. So we can write 0.375 times the initial activity equals A0 E minus lambda t. So the A0's cancel. Then we can log both sides, so end it with log of 0.375 equals minus lambda t. So minus lambda is what we calculated earlier, so 0.1208 times 10 to the minus 3 times time. So we just need to do log of 0.375 divided by minus 0.1208 times 10 to the minus 3 to give us the time, and that should give you a time that's equal to 8,120 years. If you got that, well done. Hopefully this has all helped. Thanks for watching, and I'll speak to you soon.